this one? It is. Gotcha. Right. So on Canvas, you should see a page not unlike this one. There's really 3 pages that you should probably want to look at. In no particular order, this one here, if you click on it, it's a PDF. And a lot of the sections in Chapter 7, you're going to be using the unit circle and especially all these different formulas that I'm scrolling by really quickly on. So I strongly suggest that you print these guys out and have them ready for you and for the test. You know, a simple thing like your unit circle is kind of invaluable if you've got that handy. Second place that you'll find some good resources is Chapter 7, for instance, and then you can go down and there's a similar one, you know, for the earlier chapters as we went through those. So let's look at this fella here. If you click on this, you'll see a list of some videos. So you'll find some there. If we click on the PDF files, you will see examples of homework questions. In particular, here is 7.5 homework. What I've done is I've done every single question in 7.5. And so if you get stuck on a question, you should be able to find another guy who's very similar to that one. And hopefully that'll give you some help. So that's a second place where you can get resources. And hopefully last but not least, if you then go to Sim Office and Classmates and you scroll down to our week, which is week 6, and you click on this, somewhere here, you will find our Zoom meeting. So if I go over something and I was a bit quick, or you wanted to say, I wonder how he said that, it made sense, I want to see it again, then you can go here and, you know, you can skip through videos to skip by the bit that you don't find useful, and you've got that. I've also got other things down here as well, so, you know, look through it. There's lots of, I think anyway, lots of useful information that will help you in the coming test. Are we good? Right, now, let's stop sharing. We'll start with the usual. Has anybody got a particular question they'd like me to go over, or a topic or an idea? And we'll do that. Otherwise, I have some I'll do instead. I prefer a question from you, of course.
I have question from 7.1
Sure.
homework.
Yeah.
Where it asks us to put in terms of sine u plus cotangent u times cosine u.
Sine u, cotangent u, anything else?
It's sine u plus cotangent u times cosine u. Oh.
Right, that guy. Does that look right?
No, it's...
No. There are other versions of it. Is it this one?
Yes. Wait, no. There's no... It's cotangent u times cosine.
Right, let's start from the beginning as if I've never done it before, and tell me the first thing you write down.
Sine u.
That's all I need to know right now. Now, what do you want me to do next to the sine u? Anything at all?
You're supposed to add
Okay.
cotangent times sine, times cosine. Yeah, there you go.
There we go. That's it. Right, so you're basically going to be simplifying this question, and we're going to take this fella, and I'm going to recognize that the cotangent can be written in terms of sines and cosines. And do you know off the top of your head what the cotangent of u is if you write it in terms of sines and cosines?
Cosine divided by sine.
Agreed? Now, this is going to become sine u plus cos squared u over sine u. Now, at this point in time, you could easily say, I'm done. I don't know where to go. But we have to keep going and try and make it much better and nicer. Now, what I basically got is a term and a fraction. So I want these two things to be joined together, which means I'm going to have to turn this sine u into a fraction that has a denominator of sine u. So the way I'm going to get that is by multiplying it by the special version of 1 sine u on the top over sine u on the bottom. Now what that gets me is sine times sine is sine squared u over sine u plus cos squared u over sine u. Now, can you see that since they now share the common denominator, I can make one fraction out of them? I can now have sine squared u plus cos squared u over sine u. Is there anything in that top that can be simplified? Do you recognize sine squared u plus cos squared u? Because it is equal to something really nice.
1.
Now, I believe you said that the answer should be written with only signs in it. And in that case, that's what they're looking for.
Okay.
Are we good? Our next question. Someone got a question. If you have no audio, if you type it in under chat, I'll try and make sure I get it. Madeline's having some issues. Okay. What have we got now? Any question? Otherwise, I'll pick one of my own now.
I have another one.
Okay. Since no one else has asked, I guess we'll use you. What you got?
Secant theta minus cosine theta divided by sine.
So it's another one of these simplified expression kind of thing, turn it into one variable, whatever. Right. Can't do anything about sine, can't do anything about cosine. I can do something about secant. Do you know that the secant of theta can be written in terms of cosine? Right. It can be written as 1 over the cosine. That means that we now have this really ugly fraction. Now, my goal is to try and make it less ugly. So I'm going to multiply by a special version of 1 cosine theta times cosine theta. That gives me sine theta on the bottom times cosine theta. And on the top, that guy times cosine gets me 1, and that guy gets me cos squared theta. So far, so good. Now, it's all about being able to recognize a trig expression that can be written in another format. So, for instance, knowing that secant theta can be written as 1 over cosine theta was helpful. Here's another one that's also helpful. Do you know that 1 minus cos squared theta can be written in terms in a different way? 1 minus cos squared.
Sine squared.
You nailed it. Now, do you see that my fraction is slowly but surely getting nicer and smaller? Do you notice that there is a sine squared and a sine, so I can cancel a little bit? And that leaves me with just one sine on the top and 1 cosine on the bottom. And that might well be the answer, but I suspect it's not. Do you recognize that sine theta over cosine theta can be written in a different format, a nicer format? What is it then?
Tangent.
And now you're finished. So the trick to doing this type of question is to turn everybody into sines and cosines, and then working what you've got, slowly but surely, reducing it and simplifying it until, if you're really lucky, you end up with something as nice as tan theta. Okay, I'm going to choose the next question unless we have someone different who has their own question first. Are we good? No specifics? Okay. Let me look at a couple of different solving trig equations, some of the more difficult ones rather than straightforward ones. Let's look at that one. Sine square theta plus 3 sine theta equals 0. Now, if you're going to solve any kind of trig equation where there is powers of sines or cosines, then you're going to have to factor it. This one I've chosen is quite a nice one. Do you notice that you have a common factor of sine theta? So I'm pulling that out as a common factor. What that does is it now gives me that if you want the whole thing to be 0, the sine of theta is 0. And another possibility is that the sine of theta plus 3 could be 0. And we'll look at each one totally isolated from the other. What angle gives you a sine of 0? And there are actually 3 of them. Well, there's more than 3, but there's 3 I'm looking for. In the 0 to 2 pi range, sine of theta equals 0 happens where? Anyone? If you go to your unit circle then, if the sine of theta equals 0, isn't that just another way of saying the y coordinate is 0? And if you look at where is the y coordinate 0, you get an answer there at 0. You get another answer here at pi. And then if you come back to the beginning again, you get a third answer at 2 pi. Actually, you could keep going forever, can you? 3 pi, 4 pi, 22 pi, 25 pi. Every time you get to the next place, you would get a solution that worked. Now, let's pretend that this question wanted the general solutions. The general solutions kind of have a format that looks something like that, right? Actually, they just put a plus on there. So if you ever see give your solution in the form theta plus 2 pi k, that's a generic way of asking it. They want the general solution. Now, what is the period? Of the sine of theta? I get the feeling I'm in the house all on my own and there's no one there. Has anybody?
1.
So
I'm not supposed to answer.
The sine of theta, what is the angle, what's the period of a sine of theta or a sine of x or a sine of any variable? Just a single variable. Last chance.
It's 2 pi.
Yay. Yes, just now, this fella here, if you add 2 pi to it, you'll get a solution that works. Because the way the trig functions work is if you get an answer and then you add the period to that answer, you will get another answer that works. And add 2 pi again, another period, it will work forever. We call that 0 plus the period times k. That's the generic way of doing it. So it's going to be 0 plus 2 pi k, which, since 0 really doesn't matter, there is one of my solutions. Agreed? Right, let's look at the second one. The second answer was pi, right? That works as well. If you want to get all the answers to eternity, you take the original and you multiply it by the period times k. So in this case, you get pi plus 2 pi k, and that is your second family of solutions. So this one up here, you'd get 0, and then you get 2 pi, 4 pi, 6 pi, 8 pi for eternity. And this one here, you start with 1, then you add 2 pi, that gets you 3 pi, then another 2 pi gets you 5, and then 7, and so on. If I had tried this one here, the answer would have been 2 pi plus 2 pi k, and that will not appear in the solutions. So let's write down what that looks like. Why does this guy not belong as an answer? Well, the reason it doesn't belong as an answer is that all of these are already inside that one. I mean, if you take 2 pi and you add 2 pi to it, you get 4 pi, or 6 pi, or 8 pi. They're already included. So you don't double dip. You only write down solutions that are unique to each other. And now we got this little guy over here. Well, he's only going to work when the sine of theta is -3. That isn't even a starter. Would you agree that there's no angle who has a sine equal to -3? So, no solutions out of that one. So all your answers are these two, the ones with the bubbles around them. Are we good? I need, I would prefer another question from someone, but I can certainly do.
I have a question.
Perfect. What you got?
Problem 8 from homework 7.4 is 2 cosine 2x plus 1 equals 0.
Okay. Right. Whenever you start doing the complicated ones, to me, complicated ones are things that don't just have x, but have 2x and 3 theta and 5 theta and a half theta. Things that don't just have a single variable, but have a multiple of it. In those questions, it's very important that you find the period of what we're solving here. The period of the cosine of 2x is 2 pi divided by this number, it's pi. And that is going to become important later on. That pi is going to get used. Now, I'm going to solve it the same way that I solve typical equations. As long as you do it to both sides, it's okay. So I'll subtract 1 from both sides. I'll then divide both sides by 2, and I get that. And then I'm going to think, okay, what angles have a cosine of -1/2? So I'm looking for angles whose x coordinate is -1/2. So there's going to be one up here in the second quadrant, right? And there's going to be another one down here in the third quadrant. And so you're going to go and you're going to look at your unit circle, and you're going to find the 2 different angles that have a cosine equal to -1/2. Does anybody know, say, the angle in the second quadrant that has an x coordinate of -1/2?
2 pi over 3.
Just checking that in my own brain. Looks good to me. And what's the other answer, the one that's in the third quadrant then?
Four pi over 3.
Right. Now you should be comfortable if you've got a unit circle in front of you, it's not maybe what's not happening right now. But if you have a unit circle, it's pretty easy to find those two guys, right? 2/3 pi, that's got a cosine that works. 4/3 pi, that's got a cosine that works. Now what's the difference? It's 2x equals that. Which means to get x, don't I have to divide both sides by 2? And I have to divide both sides by 2. And now we are looking at two of the many possible solutions to this trig equation. Let's assume that this question wanted the general solution, right? The one with the 2 pi k thing in it. If they did want that, then you would take this fella and you would say, okay, it's 1/3 pi plus the period times k. And now this fella here comes into play. The period is pi. So it's 1/3 pi plus pi k. And that would get written down in your box where your answer goes. And what about this fella? Well, he's 2/3 pi plus the period times k. 2/3 pi plus pi k. And there is your second solution. So if you are looking for the general solutions, right, the one with the pi k's in them or 2 pi k's in them, this is how you get it. Suppose the question was solve for x in that interval, right? Then you don't want this, right? You want physical numbers. So you return to your question. That was my first answer, right? I know that one works. Where would I get my next one? Well, you take that answer and you add the pi, the period to it, which is pi, and you get 4/3 pi. So there would be your second answer. 4/3 pi would work. Now, if I wanted the next answer, wouldn't I just add another pi? But that's too big, right? It's bigger than 2 pi. So I don't do any more than those two with the circles around it. Now you go over here and you do the 2/3 pi. We know that one works. Now, if you want to get another one, you just add the period. In this case, you get 5/3 pi. And so there will be 4 solutions, the 4 with the bubbles around it, that you would write down as your solutions to that problem. Does that make sense? Be comfortable with that process? Moving on then. Have we got another question?
I have another question for you. From
Sure, go for it.
7.4. That would be question 9. I was a little confused with
Okay.
how to do
What
this
is,
one.
what is it you need?
3 sine x equals 3 cosine x.
3 sine x equals 3 cosine x?
Correct.
Oh, that's kind of interesting. There isn't any formula in the formula sheet that turns sines into cosines. And there's not a formula that turns cosines into sines. So I'm not going to be able to do it with the usual substitute it for something else and, you know, factor it, whatever you're going to do after that. I'm going to do something a little bit sneaky. You know, as long as you do it to both sides, it's okay, Roll. I'm going to divide both sides by cosine. Now, won't 3 cosine x divided by a cosine x just get you 3? What's another name for sine x over cosine x? What other trig function is sine x over cosine x the same as? I think I heard it. So 3 tangent x is 3. I can now divide both sides by 3, and I get tangent x equals 1. Oh, do you know if this question wanted the general solution or did it want numbers between 0 and 2 pi? Can you remember?
It wants a smaller theta value and a larger theta value, and then it
Okay,
wants
so
you to use a calculator to solve the equation in
well,
the interval.
okay, in this question here, I got lucky because the numbers actually I can do it without the calculator. But since they want a calculator, let's do it. And the reason that's going to be the case is that you got really lucky with the combinations. Do you know this could have been 5 and that could have been 7? In which case you couldn't have used the unit circle. So let's pretend that we got a horrible answer instead of 1. You know, like the tan of x is 4/3, right? Something like that. How would we go about making that happen? So I'll share the screen, show you. I want to know what the inverse tan of 1 is. So I'll make sure that I'm in radians. And then I'm going to go inverse tan of 1. And that will give me the answer 0.785. And that's the small answer. Like the first one. So far, so good. Now it gets a bit uglier. If you can imagine your unit circle, and you found the tangent of 1, which is here, and the angle happens to be 0.785 radians, which is fine. That's the answer in the first quadrant. Which other quadrant is the tangent positive in?
Quadrant 3.
I think I heard it. Third. Right. Do you remember doing those weird things called reference angles? And you might say, when am I going to use them? So here we're going to use them. That angle in there is 0.785. The guy that I want in the third quadrant is over here. His reference angle, which is the angle that you make with the x-axis, is always the same. The reference angles for angles that are the same as each other is the same reference angle. So 0.785. Now the angle I want, the one that I guess we'll call the big answer, is that one, right? Now, how can I get that second answer? Well, I know what this little piece is, right? Just this little red piece. Won't that piece here be pi plus that extra little piece? So my second answer is a reference angle 0.785 plus pi, and that comes out as, I don't know, 3.141, 0.78562. About 3.92. At least that's what my brain is telling me. So there are your two solutions that are based on the inverse tan. There are going to be two answers in the range 0 to 2 pi for everybody, with a very few minor exceptions, you know, like 90 degrees or something. Okay, I want to show you one of my own versions of questions that people have had trouble with. Suppose you're trying to solve an equation sine x plus 1 equals cosine 2x, and you're being asked to do this fella using your calculator. And to get the answer to, say, 3 decimal places. So that's our question. Solve this equation in the interval 0 to 2 pi and do it on your calculator. So here goes. So here I'm going to type in the sine x plus 1. And next to it is a separate y2, the cosine of 2x. And then I'm going to do a window. And the window is from 0 to 2 pi, because they told me in the question that it was. So y1, the left-hand side of the equals, y2, the right-hand side of the equals, the window 0 to 2 pi, then hit the zoom button, and I like zoom to fit, which is zoom 0. Now, can you see in this question that the two different functions, the blue and the red one, intersect or meet at various places? It meets there, it meets here, it meets here, it meets here, and then finally I think it meets here, right? So there's quite a few places, right? And we want to write down what all these solutions are, let's say to 3 decimal places. I'm just going to find one of them to show you how to do it. You see this one here, the arrow on it? Let's do that guy. So you go second calc. So second calc. The menu choice is number 5. And now it's going to ask for first curve. Right, as I move my little cursor around, can you see I'm on the blue sine x plus 1 curve? And it's asking me for the first curve, so I'm going to say, yeah, that is the first curve. Now we're now on the red cosine 2x guy. And as I move my little cursor around, you see we're on the sine one. So I'm going to hit enter. And now it says guess. So what I'm going to do is I'm going to move my cursor as close as I can to this one, because that's the one I wanted the answer to. And once I think I'm comfortable about how close I could get, I'll hit enter. And the answer will be 3.665. Now, can you imagine that you could do it for all the other points and then you just put them in as a list with commas and you're pretty much over with? So if you want to solve an equation using your calculator, you'll have a guy on the left, the first fella. You'll then have a guy on the right-hand side, the second fella. You pick the window, whatever it is, you zoom 0, and then you go to second calc, choice number 5.
Can you slow down?
Oh, well, I'm just repeating the process. So if you watch the video, you can pause it every step. Right, so I'll try to do that again. Second calc, number 5, intersect. And then it's just going to ask the same questions again. Now, I just found that one, right? So let's find, let's find this one over here. Let's find that one. Right, I'm on the blue first curve, yes. I'm on the red second curve, still yes. And then I move it to guess. And it's like the second one is 5.760 if you round it off to 3 decimal places. In a question like this, if this appeared on the test, there wouldn't really be any working that would make any sense that you could show me. So that would not be a candidate for showing me working on the test. On the other hand, just randomly picking one, do you see the one that's number 9? Can you see that question certainly has some places that you could show me working for? So you got to make a judgment call on some questions. You're going to say, there's no point in writing down working. it's not going to help the process. So I'm just going to save some time and just do the answer and move on. Okay, well, it looks like we have time for 2 more questions. So has someone got?
I just have a quick question I just came across.
Sure.
When you're finding whether or not the answer to a plus or not is like plus or minus in a half angle formula,
Gotcha.
do you use what the original angle, what quadrant that one is in?
Mm-hmm. Yeah.
Okay.
So I'm giving you an example of what she's saying here in case you didn't catch it. I'm going to have to figure out one in the top of my head here. Yeah, it's not easy to do just off the spot of the moment. Okay. Suppose you were going to do it to find 105, for instance. That guy would be called half alpha, right? And then you have a formula that looks something like this, right? And our question is, do you use this original and not the double dot version, which is what this guy is? Yes, you use that one. So this one is in the second quadrant, right? 105 degrees is in the second quadrant. And isn't the cosine in the second quadrant negative? So you would be using the negative square root version.
Okay, thank you.
That makes sense. It's the original question, the cosine or sine of the original angle, that decides the plus and minus of your answer. A good question. Anybody get another? It doesn't need to be a homework question. It could be just a concept, like that essentially was most of a concept. Anybody got something like that? Okay, let me choose something then. Let's do another weird trig one. Two sine theta over 2 equals square root of 3. And this question, they want the general solution. And they normally phrase it by saying, keeps putting that plus minus, they keep saying, write the answer in that format. Now, you got to remember that doesn't mean that your answer must be 2 pi k. It just means that it must be something k, right? It might be a half pi, it might be 4 pi, it might be 2. That actually is a placeholder for the period. Anyway, back to this question here. If I want to solve this, the first thing I would do is divide both sides by 2. Then I'd get my unit circle. And I'd be saying, I am looking for 2 angles. It's not much a unit circle, is it? 2 angles that have a sine equals root 3 upon 2. So essentially, I'm looking for a y coordinate of root 3 upon 2. Agreed? Now, you end up with 2 distinct answers. Does anybody know off the top of their head what angle has a sine that's equal to root 3 upon 2?
Pi over 6. I mean, sorry, pi over 3.
Well done. You corrected yourself. So what we've got here is theta over 2 is that. There is another answer, isn't there, over here in the second quadrant, and that's 2/3 pi. So you go looking at your unit circle, you look for the 2 guys whose y coordinate is root 3 upon 2, and that will tell you the angles you need. Now, have you noticed that it's the angle is pi upon 3? So in this case, the angle was theta over 2. This one catches people. What do you need to do to both sides to find out what theta is? Do you multiply? Say again?
Multiply.
Yes, by 2. That makes sense? Multiply by 2. Might as well do this one while we're at it. Now, let's get the period of this function. And we're talking about the sine of theta over 2. If it helps any, do you know that's the same thing as a half theta? Right, theta over 2 is the same thing as a half theta. Now, what's the period? Well, it's 2 pi divided by a half. 2 pi divided by a half. What the heck is that, guy?
That would be 4 pi, right?
Yeah, it would be. Now, when you want the general solution, you take the guy that you know, and you just basically add the period times k. So in this case, it's 2/3 pi plus 4 pi k. And the second answer, 4/3 pi by the period times k. And this time, oops, you get this guy. I'll just rewrite him again because he's kind of messy. Now, do you notice that when you do the general solution, it isn't always plus 2 pi k? Can you see in this case it's plus 4 pi k? Maybe the next question, the period is a half pi, so it'll be plus a half pi k. Maybe the next question after that, the period is 2, in which case it'll be plus 2k, and so on and so forth. So, general solutions. Well, I know your time is very valuable. Is there anything I can do in the last 5 minutes, or are we finished for today? Is there another question or topic you'd like me to go over before we close? Yes, this is where we say last chance. Mm-hmm.
I was wondering if you could just do like one really, really hard question. That way, in case we get a hard one, we would kind of know what to do.
Oh, there's so many. I'm trying to think of what one would be considered harder than the next one. And
Like has more steps to solve before.
yeah. What I'm going to do is kind of a version of that. I'm just going to show you one that's done. And the PDF of it is online, so you can go and look at it, so you don't need to write frantically, because it would take me more than the 4 minutes that we've got left to show you. So here is the question where you were being asked to solve the cosine of 5 theta, take away the cosine of 7 theta equals 0. And I believe the question gives you a clue, and it says using the sum to product formula or something. And that's what we're doing here. So you look up the formula and it tells you what the cosine of something take away the cosine of another thing is. I believe the formula, it's cosine alpha take away cosine beta. And it ends up being -2, the sine of the two things added, divided by 2, times the sine of the two things subtracted, divided by 2. So you add these two and half it, you get 6 theta. That's a 5 underneath there. So when you combine these two and divide by 2, you get -1 theta. And that -2 is there because it is there. And then you go from this line to here. And you'll notice that that negative is gone and so has that negative. And the reason that happened is that the sine of negative theta is equal to negative the sine of theta. It's called the odd-even property. That extra negative cancels out the negative that was already here, and that's why that became positive. So we've now got two things multiplied together, give me 0. If you take the first one, you're trying to solve when is the sine of 6 theta 0? Well, if you look at your unit circle, there's lots of answers, but I'm just picking in the first one, which is 0. And if 6 theta is 0, divide both sides, theta is 0. And then the general solution is 0 plus the period k, 0 plus a pi over 3k, because the period of sine 6 theta is a third pi. 2 pi divided by 6 is a third pi. And this guy simplifies as that. Now, if you then go to the next one, which is 6 pi, 6 theta equals pi, you get a 6 pi. If you add the period to it, this is the general solution. If you went to this one here, you end up with essentially the same answers as the ones over here. So I don't really need those answers. And so the only two solutions that really matter are these two. And
Okay.
all these solutions are inside these. And that is us for today. So as I've said to the other classes, I will not be available on Monday. It's our day off for everyone. You can choose what you want to do, work or not. But I won't be available to answer emails. I will be available on and off Saturday and Sunday. So if you have a last minute question, if you need a Zoom meeting or something, we can work something else out. Although I might not get to you right away, as I have other things to do over the weekend as well. That's it. Any questions before we go? Anything you need to know before we close off? Well done. Thank you for turning up, and I shall see you on Tuesday, if not before.
Have a nice weekend.
You too. Have a nice weekend, everyone.
Bye.
Bye.